Welcome back to the classroom. My name is Mr. Wong, and today we'll be covering a question from Module 7, Inquiry Question 2. This is from the 2020 HSC Physics paper, Question 27. It is worth 4 marks. The following apparatus was used to investigate the light interference using a double slit interference, or using a double slit. You can see here, you can see our interference pattern here. The distance y from the slits to the screen can be varied. So this distance here can be changed. The adjustment screws S vary the distance d. The length of the laser can be varied across the visible spectrum. So we can change the wavelength. The diffraction pattern shown is for a specific wavelength of light. So this one that we see here. Explain 2 methods of keeping the distance between the maxima at A and B constant when the wavelength of the laser of the light is reduced. Okay, so there's a couple of important equations to look at. The first equation we have is the displacement of these gaps, or the displacement between the maxima and minima, based on the angle or path difference. This one is in your formula sheet. You can see here. If I want to find the specific maxima or minima, I know the wavelength, and then I can work out the distance, the path separation, and then I can work out the angle of difference there. There's another equation. This one is what we call one of the hidden formulas. And you can work it out this way. So we can write it as n lambda d equals to x over L. Okay. Now this x here actually represents the distance between one maxima to one maxima, or one minima to one minima. This L we have here is actually the label for the distance in length of which the screen and the diffraction pattern is away from each other. So these are some equations we can actually use. So let's actually look at the question again. We want to explain 2 methods of keeping the distance between the maxima and minima constant. So we want the maxima and minima to be constant when the wavelength of the laser is reduced. So we can actually use this equation to help formulate our understanding. So I'm just going to write down the formula. Okay, and if we look at the distance, so x is the thing we're trying to find. So assuming, let's just say assuming distance between maxima A and B are constant. That's the following equation that we have here. Okay, if we rearrange it and make x the subject, because that's the distance in separation, and you don't really need to write out again what it is, because, well, so long as you've actually labeled it on the diagram here, that will be fine. And L, D in separation there. Now, if the wavelength has been reduced, according to this equation, we can increase or we can decrease the distance in variations between the 2 slits, or we can increase the length of which the screen is separated. So we can make this bit smaller, or we can make this bit longer, according to our equation here. Okay, so let's just go through. I'll write down each method. So method 1, that will be to decrease the distance between the slits. Okay, that's our first method there. And method 2 would be to increase the length of separation. So what we could say is increase or decrease the value of D. Here we want to increase the distance between the slit and our pattern, which means we are trying to see an increase in Y. So I'm going to change this to Y because that's what the equation in this question is also using. So I'll change that to Y instead. Okay, so by doing that. Okay, I guess the next thing we can just quickly mention is what is the explanation why doing this would work, and we can use this equation that we drew up here to do that explanation. So the assumption is x is constant, so x is constant, okay, and we already know that lambda is decreasing, lambda decreases, then we can see that x is inversely proportional to d. So by decreasing d, I will increase x. So hence a increase in x comes from a decrease in d. Same thing here, the assumption is that x is constant and there is a decrease in lambda. We'll also write it sort of like this so it makes it very clear. So x is proportional to lambda and also times the distance of separation. So we're assuming that x is a constant, all the other variables are constant, so we'll also say that n and y are constant. So you can assume they're like a value of 1. And same idea here, we can assume in this case n and d are constants. So by that, this is the equation we have. If I want to increase x, I'll have to increase y, because y we can see is directly proportional, while as d on this hand is inversely proportional to what we're trying to get. Okay, I'll zoom out a little bit. Okay, so just a quick recap. By increasing the distance of separation, so we increase this one here, we can maintain the gap difference between band A and band B, or we can decrease the distance between the two slits, and that will also maintain this gap, assuming that we are seeing a drop in the wavelength of the laser we're using there. Hopefully that gives you a better explanation of how diffraction patterns work. I'll leave it here. My name is Mr. Wong. If you found this video useful, please give it a like, and I'll see you next time.